Welcome to Gradient Boosting. This is part 6 of Ensemble Techniques, and in this video we shall cover the 8 mathematical steps of a gradient boosted algorithm. Okay, so let's get started. The first fundamental idea behind gradient boosting is we will be building an ensemble of trees based on the gradient of the loss function, and iteratively we learn to solve tougher problems. Okay, so first let's get going with the algorithm, and then we'll explain more and more as we go through each of the steps. First, we have been given an input data, and here we have been given x and y, where I is running from 1 to n. So n data points are there. X is independent variable, y is our target variable, which is the target features. We also have to have an input on a decision on the loss function. So in the boosting video, we had covered 3 of the most essential loss function with respect to regression. And one of them we had touch based was the mean squared error. So in our context, we will use mean squared error as a loss function. However, if you have to revise that, I would recommend you go back to the boosting video and then review all the loss functions in it. Now let's move on to the first step. Now that we've been given data and a loss function, what we're going to be doing is we are basically going to be creating a base model, which is creating an instance of the decision tree if we're going to be using a tree-based algorithm, which is the context of our discussion. And we'll build the tree using the input data, optimize it for the loss function which we have chosen. Okay, and as part of that formulation, we do see that it is taking in the actual value yi and also a gamma parameter, which is in this initial run would be the xi, or the independent features given to us in the data. The next step is where the ensemble process actually starts, because the process starting with a loop where m indicates the number of trees we would like to have, and typically in a gradient boosted trees algorithm we have 100 to 200 trees. The step 3 is where we are calculating the gradient. If you look at the function, this is a partial derivative of the loss function we have chosen with respect to the function that we are actually using to predict the value. So which means the model which is taking in our independent features. Okay, so the idea here is we are measuring how much the loss function is changing with respect to the change in our model's output. Okay, and it is also worth noting that we have a negative sign out here, indicating very clearly this gradient is a gradient descent. That's what we are trying to do, because we want to minimize the gradient. Okay, all right, so the f of x here, just to get the notations right, is this is a loss function, partial derivative of loss function. Y is the actual values, f of x is our function with which we are trying to predict the actual value. And here in the initial case of f of x, it's going to be the base model, because if it is running the first time, it would be f of 0 of x, which is what we saw in step 1 as the base model. Okay. Going on to step 4, here once we have the RIM, which is for each of the data point you've calculated that, what we will do is we are now trying to build a new tree on the gradient itself. So the earlier tree f of 0x, which was calculated in step 0, had fitted the data on xi and yi. However, here we will be fitting the data on xi and rim. Okay, so that's a key difference. We are not using yi here anymore for this new built up tree. The next thing we do is once the tree has been built up, we look at creating something called as terminal regions. We group and merge all leaf nodes under the last level node and coin them as terminal regions. Okay. And in step 6, we compute gamma. What we're doing is we're calculating the loss across all leaf nodes for the last known model. And it is worth noting that if our loss function is a mean squared error, as we have made an assumption earlier, then we will end up getting an average value from the terminal regions. Okay. The gamma value calculated here also has other names like terminal regional value or the output value. Okay. Now that we've seen those steps, let's just summarize them and then come back to the important step of step 7, where we are making a new prediction. So in step 7, the new prediction is made as a sum of last known model, which is f of m minus 1 of x, plus a new, which is referring to the learning rate parameter, typically anywhere in the scale of 0 to 1, and a sum of all the gamma values that we have calculated in the previous step. Okay, so that's how the new model is being put together. And that new model is a composition of what the old model learned, plus also the composition of the residual or the gradients fit for a new tree that we have computed in the earlier steps. Okay, so finally, this loop keeps going on from step 3 to step 7 for all the m values that we have configured. And once that is complete, the model that comes out fm of x is the final model, the last formulated ensemble model that will be given as the output for the gradient boosted tree. Okay, that's all for this video. I hope you enjoyed it.